I'm in the lab. Let me change a bunch of preference here so that you guys can see what's going on. Okay. So I'm in the lab and I've got the, what we will do today is I will give you a demonstration of experiment number 4. So you guys can see exactly what it involves. So here's my setup. Okay. And the setup is, you guys should have, let me tell you what you need. You need your cobalt chloride, okay? Cobalt chloride, CoCl2. You also need your iodine. That's this right here. It's in this baggie, double container. And then you also need sand, okay? What you want to do is you want to look at these things separately. I'm just going to put it on some weighing paper so that you guys can see what these things look like. So let's take a look at this. This is sand, and the sand's going to be the largest quantity. And so again, I just want to put it here so that you guys can see what's going on. We're going to put it in here, get your observation, and then we're going to put it in a bigger beaker. Okay, we're going to put it. So this is sand. You can see that it looks like sand. And then this is cobalt chloride. It's going to be in this container. I'm just going to take, why don't I just take this? And you can just dump everything out. Okay. And look at the quantity. The sand's going to be the most. The cobalt chloride is going to be the second. And then the iodine. And again, it's in a double lock container because these things tend to be volatile. And I don't need much. Oh, I need, yeah, that's plenty, okay? But look at the quantities. And pay attention to the texture and pay attention to the color. The color is going to be the most important because that's how you're going to tell which chemical is going to be separated first. Because that's what your observation's about. You're going to mix it together and then you're going to separate it. So this is the sand. I'm going to put the sand first in this beaker. Then this is the cobalt chloride, and I'm going to put that. And it's got cobalt chloride hexahydrate. In other words, the formula is CoCl2 6H2O. In other, it's like you know those electronic those packets that you have in your electronic component when you buy one. It's called a hygroscopic component because it absorbs moisture from the air, so that the moisture doesn't damage your electronic component. Well, cobalt chloride is very similar. Cobalt chloride is what we call anhydrous. And then when it picks up the water in the air, it's going to pick up like 6 waters. That's why you put CoCl2 dot. The dot means that it's attracted to the 6 waters. And then those waters can leave or attach depending on the humidity. Then I'm going to take the iodine and put that in here. And you notice that the iodine is the lowest quantity and the cobalt chloride is the next, and the sand is the most. You guys are going to take this is called an evaporating dish, not a watch glass, but the evaporating dish. And then you're going to put some ice because you need a cold surface. Okay, got some ice right here. And then you're going to make sure that it fits over the beaker. You want to find your largest beaker, and hopefully this thing will fit. If it's too small, you need a smaller beaker. Okay, but this is the setup right here that we're going to do next. What I'm going to do next is I'm going to heat this up, and you can see it right here in my hot plate. Now you guys can certainly use your alcohol burner, but so I'm going to try and give you a close-up so you can see. What I would like you to do is follow the iodine as this thing heats up, because you want to see the iodine and the cobalt chloride. You want to see what happens as it starts to heat up. Okay, because you guys are going to be taking careful observations on that. So right now it's heating up. Yeah, you shouldn't do this, but I'm an expert on this, so I know what's going on. And it's going to take a while when this thing, but as soon as the gas start, I'll kind of tell you, or at least I'll try and help you with what is going on. Okay, but that basically is it. If you were in lab, I mean, this is basically what you would be doing, and this is what you would have to be waiting for if you were in lab. Let me go ahead and crank this up a little bit and see why it's it'll take a while just because it needs to get to a temperature where one of these chemicals is going to sublime. And sublimation is the process by which a solid, because all of these are solid, goes into the vapor directly. You can see right now that the inside the beaker is turning purple. That means that one of the chemical is subliming. You need to figure out which chemical that is, okay? And if you look real closely, you can actually see if I can't turn this around for you. Okay, you can see that there's a chemical here that actually is turning to a vapor, whereas the other chemicals are not. So that's important in your observation because the chemical that's turning into vapor, you need to identify that. Is it the cobalt chloride? Is it the sand? Is it the iodine? And you can see the gas that starts to form. That's what's going to be collecting in the cold surface. And you can see at the very bottom of this evaporating dish, starting to turn brown. And that's because when a gas converts directly to a solid, then that's called deposition, okay? Solid going to a gas is going to be sublimation. Gas going to a solid, that's called deposition. And they do that a lot in the semiconductor industry, where they have to make silicon chips for your semiconductor. And they do a lot of deposition, and they coat the surface of a wafer with these chemicals. So you can see it's really going to town right now. You can see the purple gas starting to dance down here. And then as that chemical starts to go into the gas phase, then there's less gas because there's less chemical to do the sublimation. And notice the other chemicals are there as well. Now the purple gas is clearing up, and that's because it's all collected at the bottom right here, okay? All collected at the bottom right there. And pay attention to the remaining solid. As we heat it up, look what happens to the color. This is an important part of your lab, is to make careful observations so that you can follow. What you need to remember is that we're doing physical changes in which we're converting by applying energy the characteristics of one chemical in terms of the characteristics of maybe another chemical or the same chemical, but now it has, like when you melt ice, when you melt it, turns to liquid water. It's still water, H2O, but now it has a different physical feature. So we're going to let this go for a little bit more until that purple gas clears up, and then I'll show you the bottom of the evaporating dish. And then what we do with this one right here. The bottom of the evaporating dish, if you look at your lab manual, is going to be product A. You need to identify product A, okay? So let this go for a few more minutes. The purple gas is clearing up. Don't remove this. Don't remove the evaporating dish until most of the gas is gone. Because if you move the evaporating dish when there's still a lot of purple gas, then it's going to fill your room. You don't want to do that, okay? And you also want to put it probably in a stove where you have proper ventilation, okay? You want to do that. So it looks like we're about there. But the other thing you want to do is you want to heat it up to the point where now you start to see color changes in the remaining chemicals that are left behind. Okay, remember what the cobalt chloride looks like? It looked like a violet color. The iodine looked like a gray color. Sand's just sand. But look what's happening to the remaining chemical, and I can't tell you what the remaining chemical is because that's your assignment. But look what happens to the color. Okay, look what's happening to the color of that chemical.
Professor,
Yes.
for the iodine crystal, is this the same that we used from the previous experiment?
Yeah, but you have 2 bottles.
I think I only
Okay.
have 1 bottle.
I gave you 2 containers like this that was in your baggie.
Yeah.
There should have been 2. It doesn't say 12, it says I2. Okay, that's the problem. You
Oh, okay.
couldn't
I
put a
thought it's 12.
subscript. So 12 means I and then 2.
I too. Okay,
Sorry.
no problem. Yeah.
Okay. So looks like we're done. It's pretty much clear and it's pretty much safe. So I'm going to turn off the heat. I'm going to use the hot plate again. But what I want to show you now is what you need to do is you need to remove this, and then you need to take another beaker and dump the water. Okay, dump the ice. So I'm going to do that. And then you're going to turn it upside down. Put like a napkin so it doesn't mess up your stove. And you can see right there that it's sort of metallic like. Okay. And then this one right here is the remaining 2 chemicals. And you can see again the coloration. Now it's like powder blue. You can still see the other material here that is like a beige. You know what that is. I don't have to tell you. But look at this powder blue, and then look at this chemical right here. This is A. Okay. Once you're done with A, then just kind of put it aside. Don't let anybody touch it. Put it aside. You want to take a picture, I think, of the 3 isolated substance at the end. So put this aside. You don't need the evaporating dish anymore. What we're going to do next is I'm going to put water in here, and you're going to see that one of the substance is going to dissolve in water, the other one will not. Okay, so again, that's the second. So here it is. You want a minimum amount of water. And the reason why you want a minimum amount of water is because the more water you put in, the longer it'll take to evaporate. Okay, just swirl it around. And one of the chemical B is going to dissolve, and it changed the coloration of the water. Okay, so that again, that's something that you got to write down, your observation. It's an observation that you have to write down. And then the next thing that you guys are going to do is you're going to call decant. Now look at the procedure for this experiment. There's a couple of things that it asks you. One is what property is being exploited in order to cause the chemicals to separate. You got 3 chemicals in the beginning. You separated A already. Okay. What property was exploited in A to separate it from B and C? That's one thing. Okay. And what was the technique that you use? Then we have B and C here. Put it in water. It's not separated yet because they're still there, but now it's in water, and then we're going to do a decanting, and now that separates chemical B from C. Let me get a beaker. So here's an empty beaker, and notice what I do. Okay, I'm going to take this, and the more dense material is going to stay in the bottom, but the water, which is less dense, and you guys know that the material that's more dense than water is going to sink, and then water is allowed to flow through. And what I'm doing is I'm just decanting. This is called decanting, where you're letting gravity help you separate it. Now you don't have to decant all the liquid, but certainly this chemical right here which is B, because that's being separated, is now here. Now you've got two separation. You've separated A and B. This is C, but it's not separated because it's in water. Okay, this is in water. So what you need to do next is you need to separate the water from C. And we do that by heating up the beaker, and we just we allow the water to boil away. Okay, so again, this will take a little bit of time, and I just got this thing cranked, so it's going to take probably about 5, maybe 10 minutes. So if you have something to do, then do so, but we're just going to, in real time, like if you were doing the experiment, this is what you would be looking at. You'd be bored, of course. Actually, you'd be answering some of the questions. In fact, you could probably answer some of the questions just based on this video, but you still have to do it. Okay, I want you to go through the trial because you do need to take a picture of it. But you could probably start answering some of the questions because you already have some of the observations. You could answer some of the questions already just based on what you've seen. Okay, so what I'm going to do is I'm going to allow this to heat up and start to evaporate the water. The water now is going to have it's going to be more volatile. Volatility has to do with the ease way which a substance can go into the gas phase. And because water is more volatile than substance C, you start to evaporate it. And it's okay not to collect the water. You're going to see there's some steam that's coming off here. Let me see if I can't help you see that with the background. Maybe the white background's not good. Okay, but you can see the steam coming off, but and then it'll leave the chemical behind. That's why I said use a minimum amount of water, because if you use too much, then you're going to be boiling for at least an hour or half an hour. So minimum amount is all you need. Okay, so I've got this crank up, and now it should be getting to the point where that water is starting to boil. And you see how it starts to fog up here? And that's bad because you guys can't see that, of course, but you get the idea. So give this about 5 minutes. And then what will happen is that when you get to about maybe 0.5 milliliters, half a milliliter, it really starts to form the solid. And the important thing is watch the color transformation as the residue of C, the chemical C, starts to go from the aqueous phase to its solid phase, to its dry phase. Okay, so that's what we're doing here. Now I can hear this thing starting to boil. Here you can see that it's starting to boil now. And you want to use the biggest beaker. Why? Because the bigger surface area allows for faster evaporation. If you use like the small one, like this, the surface area is so small, it'll take like a long time for that thing to evaporate, because the water evaporation is only going to be as fast as the surface area that is there for the water to escape. Okay, that's why you need your largest beaker here.
Professor, quick question about the first step earlier. Sorry, I'm not really pay attention earlier. So do we need to put our ice on the evaporating dish?
You need to put the ice on the evaporating dish.
Yes. Yes.
Because you need the cold surface. If
Oh.
you don't have a cold surface, the chemical can attach itself. It'll just escape through the side. So when this thing starts to go down, and you'll see that shortly, this is what it'll turn into. Okay, this is what it turns into. And what we're going to do is the very last step is we're going to put a drop of water just to see what it looks like when it is rehydrated, because this is in the dehydrated form. Dehydrated just means it doesn't have the water in it. And then when we hydrate it, you're going to see again some physical characteristics. In the meantime, like I said, this right here is the bottleneck of your experiment, the longest procedure. But you can see that even the experiment itself is not very long. Okay, you could probably do this if you everything's set up. You could probably do this experiment in under an hour. This, of course, will take about 30 minutes, maybe a little longer, depending on the amount of water you use. So,
Professor,
yes.
I have a question. Would it be better to use the alcohol burner outside, like in a patio, or
Yeah,
on the top?
you can certainly do that. If you just need a place where the gas that's being formed can escape. Okay. And the alcohol burner, yeah, it's gonna, you got to be a little bit more patient because that thing will, you got to make sure that it's supposed to be set up so it's going to be in the hottest part of the alcohol burner, but it's still going to be a while. So that's why you want to use minimum amount of water. That way it'll go faster. Okay. So I'm down to about maybe 3 milliliters. But again, I'll point out the critical time because I really want you to see the features that are involved in this particular process, because that's an important part of your observation. You can see right at the edge where the water starts to go into a gas, you can start to see some blue coloration, okay? And that's because some of the solid in C is, some of C is turning to a solid in the side because there's no water there. But now we're at the critical point. Now we're to the point where the last bits of water is evaporating. And again, it's important to see what the transformation looks like.
Professor, I just wondering if we can use the, like portable electric.
Yeah, you can do that.
Yeah. Okay. Okay.
Yeah,
Because
you just need a heating source.
Yeah, I just worry if we burn the, what call.
No, your beaker should be non-flammable. Okay, just make sure that your beaker doesn't have any stars. If it has stars or stress, once you heat it up, it'll break, it'll crack.
Oh, okay. Yeah.
Okay, so
Okay.
you always want to inspect a glassware by looking at the very bottom and look for stars. If there are stars, that's a stress on the glass. You heat it up, it'll break because things tend to expand when you heat it up.
Yeah.
And when glass expand and there's a star there or a stress, it just cracks, breaks
Okay.
it up.
Okay, maybe I try using the electric stove.
Yeah,
Maybe the small
that'll
one
work.
is not the big one.
Just put in a low setting initially.
Low setting. Okay, sure.
Okay, so we're coming down to the last, and you really should be using tongs if you have it. Okay, so you can see and practice using it first so you don't like pick things up and drop it, because I've seen a lot of student in lab try and pick it up with a tong, try and do it this way, and then it just messes things up. They break the glassware, then they have to start the whole experiment. Look at the center. See how the center's turning powder blue, like the chargers, the former chargers? Well, that's the color that you want to make that observation. Okay, so what I'm going to do is at this last bit, I'm just going to turn off the hot plate and allow the heat from the hot plate to evaporate the rest. Okay, that's all you really need to do, because if it's bone dry, there's nothing there, then you start heating up the beaker. The heat is not going to be transferred to the water anymore. Right now, the beaker is hot, but it's not that hot because all the energy from the hot plate is going to boil the water. That's where the energy is dissipating. If there's no water there, then that heat is going to transfer to the beaker. And when you get the beaker too hot, then it's going to fracture. So again, I just turn off the hot plate and I allow the natural heat from the hot plate to evaporate the residual water. And I think I put that in the directions as well. So here you can see exactly what's going on. Okay, you can see exactly that this is turning into this. Okay, it's turning into that. Note the color. Okay, note the color. The edges is powder blue, but then the center is kind of like violet. I don't know. You guys have to describe that color. Okay, it's not purple. It's not violet, but you guys can see. Okay, you should use yours. So we're pretty much done here. Okay, the water has completely evaporated. I'm going to take out the hot plate so I don't get burned. Okay, let's take a look at this right here. First, I'm going to take the dry one. So see, it's hot. It's heated. It's got no water. This one has been sitting around for about an hour. And what has happened is that the chemical that was this is now picking up the water in the air, because we've got water in the air because of the humidity. And when it picks up the water in the air, look what happens to the color. Okay, I'm going to accelerate it a little bit by adding a drop of water here so you guys can see. You can see what's going on in terms of that. You can see right here. Again, the color is starting to change. Like that. Okay, let's do it on this one where it's blue. It's blue. I'm going to add a drop. And you can see that as I add a drop, it goes from that powder blue to that more violet, well, kind of like light purple color. Okay. So that's what I'm doing. I'm just adding drops here and hydrating it again. Okay. And that's basically your experiment. That's it. Now you can take this, you can take this, and you can take this, which is A, B, and C, and you can match it up to which one's cobalt chloride, which one is sand, okay, and which one is iodine, right here. So that's the 3 before separation, the 3 before separation, the 3 after separation. Okay, pretty much is the lab. You guys have any questions on that?
We clean up with the regular water.
Yeah, clean up with regular. What you want to do is just take this, put water, swirl it around, put it in your waste container. Swirl this around, put it in your waste container. This one, let me show you how you would do this. Just take this, put it over a beaker, and then just wash it down with water. Wash it down with water. It'll wash down easily.
Okay.
Okay. And then just take a paper towel and then wipe it dry.
Same thing for the beakers. Do we just wipe it down?
You can just, once that's done, then you can just wipe it down and it's clean. Okay.
And the beakers?
What was that?
The beaker, do we, after we rinse it, do we just dry it out with the?
Yeah, just make sure that like most of the chemical, use your water bottle to kind of like spray it. And then as you spray it, then in the mouth of the your waste container, you can just allow it to drip in like that. Once you get most of it out, then you can just wash it with soap and water.
Okay.
Okay. Thanks for asking.
Well, thank you.
Okay.
Professor, one question, Professor.
Sure.
I think this will be in one experiment that we will use the distilled water. So for the distilled water, should we use just like regular drinking water?
Yeah, if you get bottled water from the store, not tap water. Problem with tap water, it's got too much chlorine and it's got calcium.
Okay.
Okay,
Yeah.
that's the white stuff in the water. When you allow it to evaporate, if you're boiling water, you don't want that because that'll contaminate your experiment. But drinking water is fine. They don't add anything there,
Yeah.
and that's perfectly fine in terms of using that.